Hi, I'm Niema Moshiri. I'm an assistant teaching professor in the Computer Science and Engineering department at UC San Diego. So for today's workshop, I'm going to be going over how do you run a viral sequence analysis workflow. I'll be showing you what tools I'm using. I won't go over how to install those tools. I'll kind of just point you to the tools and let you figure it out on your own system. But I'll show you how to use those tools to do a viral analysis workflow. So first, what's the motivation? So I'm sure everyone watching has been impacted by the COVID-19 pandemic in some way. And one of the ways that epidemiologists can fight a viral epidemic is using the evolutionary history of the virus. So since the sequencing technologies have become cheaper and cheaper over time, it's becoming more and more commonplace to do sequencing of viral samples from patients. So here I'm showing you this report from this group called NextStrain. Normally they do influenza and other viruses, and during the COVID-19 pandemic, they've been giving a real-time report of COVID-19. And you'll see that here we have the evolutionary tree of a bunch of different SARS-CoV-2 sequences, SARS-CoV-2 being the virus that causes COVID-19. Basically, an evolutionary tree, the tips represent individual samples. So I can highlight one and I can see this sample came from Singapore. It was submitted on August 2nd, 2020. And then kind of internal nodes, as you go up the tree, these are ancestors that we're inferring. So basically, if you were to estimate the evolutionary history of viruses and then overlay metadata about the individuals, in this case, they're overlaying continent information, you can actually track the progression of the virus as it spreads through a given community. So this is kind of the motivation. We want to be able to do something like this. How do we actually estimate this evolutionary history from just the sequences? So for today's workshop, I have a data set that I will be using. I'll actually maybe show you the database you can access to find these sequences. So the sequences I'm collecting are from this database, GISAID. Feel free to look at that database if you want to access these sequences. I think you can also find SARS-CoV-2 sequences on NCBI. But yeah, this is where I would recommend checking. So for today's workshop, I'll be using an example subsampling of just 50 sequences to keep the data set size small. As you get bigger data sets, then these analyses become much slower. So here I'm showing you the 50 sequences that I have. Basically, you'll notice that the sequences don't really seem to line up very well. They don't really seem to have any matches. So each row is a different sample. You can see some metadata about them here. Maybe I'll see if I can zoom in somehow. Oh, maybe not. Okay. But you'll notice that they don't seem to line up. And the reason for this is that just naturally insertions and deletions happen as the virus mutates. And also there's potential errors in the sequencing technologies. And the sequencing technologies might not all be capturing the exact same window. Maybe some of them are slightly off by maybe 100 letters. Maybe it's pushed over than the other. So the first step that we have to do in any viral analysis is getting these sequences to line up properly so that we can detect what positions of the virus correspond to each other. So for example, what letter in this first sequence corresponds to what letter in the second sequence, etc. This problem is called multiple sequence alignment. So the tool that I'll be using to do this is called MAFT. Let me share my terminal screen. So MAFT is a tool, M-A-F-F-T. It's a tool for doing multiple sequence alignment. Let me just call it with -H. So MAFT, the website, can be found here. If you just Google MAFT, you'll be able to find the website. Basically, what this tool takes in is a set of sequences that are not aligned, and it will estimate a multiple sequence alignment for you. So my file is called SARS-CoV-2.FASTA. What I'll do is call MAFT For my purposes, because I'm going in kind of blind, I'm not assuming anything about the data set that I have, I'll use the auto functionality of MAFT to let MAFT pick whatever the appropriate parameters are for me. And MAFT also supports multi-threading to speed up my program's execution. So on my laptop, I have 8 cores. So I'll specify --thread 8 to get a little bit of speed up. Looking at the usage, I specified the input file, which in my case is SARS-CoV-2.FASTA. And then I can redirect the output. So normally it prints the alignment to standard output. I'm going to just redirect it to an output file, which I'll call SARS-CoV-2 maybe maft.aln. I personally like using the ALN suffix. Oh yeah, let me actually maybe show what do these files look like. I showed it in the editor, or like in the viewing tool, but let me just pull it up in a normal text editor. So the sequences are just in the FASTA format, which is a plain text format. Basically, you have a line that's a header. It starts with this greater than symbol, and then you have a sequence. And then you have another line that's a header, and then you have sequence. So they're all just plain text files. What you choose as the extension is really your own choice. I just personally like using ALN extension for representing an alignment. Okay, so this is how I'm going to run the program. I'm going to run it, and then math takes a little bit of time. So it's outputting the progress. So we see it's finished the first progressive alignment, just one of the steps of the multiple sequence alignment algorithm. And then we just kind of wait for it to run. It's going. Okay, now it's on the second progressive alignment. So this is towards the end of it. Okay. Almost done. There we go. So now we finished aligning those 50 sequences. So I just want to maybe pull up what they look like. So if I open them, it split it onto multiple lines. That's fine. But you'll notice that, You'll notice that MAFT has inserted these dashes. This is to help the sequences line up better. So I'll open them in my other viewing tool. Let me switch to my other viewing tool. It's loading. Okay. So let me share that screen. And by the way, I'm using a tool called JalView to view the sequences. This is kind of a standard tool just for visualizing. You could use any text editor, but what's nice about JalView is that it's just aesthetically pleasing. It's nice that it has these kind of viewing features, and it shows the frequency of each nucleotide. But what you'll notice compared to before, so let me actually also open the original sequences. It's loading. So what you'll notice is the original sequences, which are here, they're not very lined up, right? So what the multiple sequence alignment has done is it's taken our original sequences and has now lined them up nicely. This is the first step that any tool that infers evolutionary histories needs to have. It needs to have the sequences lined up. Okay, so this looks nice. My sequences are looking good. Now for the next step, I can actually predict the evolutionary history from this multiple sequence alignment. So I'm going to switch back to my terminal. The tool that I like using is called FastTree. It's fast. It's not as accurate as some other tools. So one other tool that I would recommend is called IQTree. IQTree is generally, the help message pulled up a lot more than I was expecting. So IQTree is generally considered to be more accurate in the trees that it gives you than FastTree is, but it's also much slower. For the purposes of this workshop, I'll just do FastTree because it's nice and fast. So let me just call it with -h again, so now we get it down here. So FastTree takes as input, so I call FastTree. The -nt parameter specifies I'm dealing with nucleotides, because this is a nucleotide sequence. I'm not looking at a protein sequence. I would specify -gtr, which is the model that I'm using. It's the general time reversible model. This is generally what model you want to use for estimating an evolutionary history. I'm going to specify -gamma, which I won't go into too much detail about what this is doing, but it basically, it allows you to have different rates of evolution across different positions of the genome. What that means isn't super important, just these are the 3 parameters that I generally use when I run FastTree. Okay, and then I specify the alignment. So my alignment was called SARS-CoV-2.map.aln. And then I specify where I want the tree to output. So I'm going to output it as SARS-CoV-2.map. Or maybe I'll call it, .map. FastTree.nwk. This is just some arbitrary output file. And now FastTree starts running. It shows me its progress. So it's saying that it's running using OpenMP for multi-threading. It's using all 8 of my threads. It gives me some summary statistics. And then this is the current progress. So it's optimizing the GTR model. Remember, we specified GTR. Now it's optimizing the site likelihoods. This is the -gamma option that we had done. Okay, and then it's doing one final set of optimizations, finishing up. These tools are generally pretty slow. This is only 50 sequences, and it takes, in this case, it took almost a minute. Now imagine what would happen if you had 80,000 sequences like we currently do for COVID. But alas, it finished. That's nice. So the output file, let me just show you it in my terminal briefly. The output file is a representation of a tree in what is called the NUIC format. So that's why I just specified the extension as .nwk for NUIC. The NUIC format, just like the FASTI format, is just a plain text format. So I could have used any arbitrary file extension. I just like using .nwk because it reminds me, oh, this is a NUIC tree. How do you interpret this? Well, it's not very obvious just from looking at it. So instead, what you can do is use a tool like, let me stop sharing my terminal. How do I actually visualize this? I like using this tool called Phylotree. If you just Google Phylotree, you'll probably find it, but the URL is here, phylotree.hyphi.org. They show you an example tree just to let you see how to use it. But in my case, I want to specify, let's see, the NUIC tree that I created. And here we go. This is now my evolutionary tree. You'll see that as with the big tree that I had shown you, each of the leaves represents one individual. So this sample came from England, this sample came from the Netherlands, this sample came from Denmark. You can have different drawing styles. I can draw the tree as a radial tree if I want. Let me go back to linear. I can kind of expand the tree to space it out a bit. You'll see here I have a little ladder to help me keep track of the height of the tree. And yeah, so then the next steps would be if I had any metadata, I could overlay that metadata onto these. So let's briefly look at this. So you'll notice that these England sequences are kind of all grouping together. Then we have a Malaysia sequence. We have a couple Scotland sequences next to each other. So ideally, what we would hope is that sequences that are coming from a similar source of infection should cluster together closely in this tree. And we do see that, based on this kind of small subsampling, we do roughly see this. Yeah. So to briefly summarize, the tools that I used were MAFT. If you just Google MAFT, you'll find it. MAFT was the multiple sequence alignment tool. Then I used FastTree, which is the phylogenetic inference tool to actually estimate the evolutionary history from the tree. I used PhyloTree to view the tree, and I used JALView to view the sequences. So these are the 4 tools that I would recommend for this. And remember, I mentioned FastTree is a little bit less accuracy. It's just much faster than some other tools. So if you want a more accurate tool, but slower, I would recommend IQTree. So yeah, that's how you go from raw sequence data to an estimated evolutionary history.